All right, so here's the first example that comes across in your book, and it is on page 458. It says an air track cart attached to a spring completes one oscillation every 2.4 seconds. So that would be its period right there. At time equals 0, the cart is released from rest at a distance of 0.10 meters from its equilibrium position. What is the position of the cart at A, 0.6 seconds, and B at 1.2 seconds. So here's a picture of this spring attached to a mass. It's on a frictionless, it's hooked to a cart here that has a mass on this frictionless surface. So it's being held here, and when it lets go, the spring and the cart mass move this way and go back and forth from here to here. So here it is at its initial position. This is time equals 0 right here, and the spring has been pulled to its amplitude of 1/10 of a meter. So once it lets go, it's going to travel this little cart. The first segment is going to be from here to here. And that'll be the first segment. And then, of course, it continues to move, and it moves over here to this point. And then it comes to a complete stop, turns around, and comes back in this direction to its equilibrium point, and then back to the point it started. So think about taking that whole motion and splitting it up into 4 sections. And each of those 4 sections are equal time. So it takes 2.4 seconds for it to start here, go all the way to here, turn around, and come back. So each of these little segments, if you think about time divided by 4, it took 2.4 seconds to make that whole motion there and back. So 1/4 of 24, think of 24 divided by 4 is 6. So it's going to take about 0.6 seconds for it to make each of these little segments. So from here to here's 0.6, from here to here's 0.6. So to get from here, time equals 0 to here, would be 1.2 seconds. And then here to here would be another 0.6, so that would be 1.8. And then the last segment would get you to 2.4. And so if you just look at that problem conceptually, time equals 0. 0.6 seconds, 1.2, 1.8, and 2.4 until it gets right back to here. So the question was, what is the position of the cart? What is the position of the cart when it's at 0.6 seconds? Well, it's at 0.6 seconds right here, so it's at its equilibrium point. So what is x at 0.6? It's x equals 0, the equilibrium point. All right, where is the cart at 1.2 seconds? At 1.2 seconds, the front of that cart is going to be right here at x equals negative 0.10. In other words, 1/10 of a meter past the equilibrium spot. And then from there it bounces back. So it's at 0 and negative 0.1 are the 2 answers. That's shown right here. All right, on that same page, underneath that problem, we have problems 5, 6, and 7. 5 says, what is the amplitude of the cart's motion? What is the amplitude for the cart's motion? Well, remember what amplitude means. Amplitude means how far, what's its maximum displacement from the equilibrium point. So if you go back and look at the spring, the maximum amount it's displaced from its equilibrium point is 1/10 of a meter. So that is its amplitude, the maximum amount it gets displaced. So the answer to 5 is 1/10 or 0.1 meters. Number 6. What is the speed of the cart when its position is at x equals negative 0.10? Well, at x equals negative 0.10 is when the spring and the cart turn around and come back the other direction. So in order for anything to turn around and go the other direction, it has to come to a stop. Even if it's such a microscopic stop you can't see it, it's still officially that velocity has to come to 0, just like when you throw a ball up in the air and come back down before it can turn around and go back the other way. So at this position right here, the speed would have to be 0. All right, number 7. It says a mass moves back and forth in simple harmonic motion with an amplitude of 0.25 meters, a quarter of a meter. That's the amplitude. And it has a period of 1.2 seconds. That means it takes 1.2 seconds to go through one complete cycle. Through what distance does the mass move in 2.4 seconds? Well, remember, in order to make one complete cycle, imagine that this is kind of your track. And here's the equilibrium point. And I don't know what the amplitude, does it tell me the amplitude? Yep, it's a quarter of a meter. So they pull it back to a quarter of a meter. And so we're going to start right here at time equals 0. It's going to travel to the equilibrium point. Then it's going to travel to negative 0.25. Then it's going to turn around, come back in those same two segments. So if you think about taking that whole cycle, the spring pushes all the way here and comes all the way back. That's one complete cycle. And it takes 1.2 seconds to do that. Well, how far has it traveled? It's traveled a quarter of a meter, a quarter of a meter, a quarter of a meter, and a quarter of a meter. So down and back, it's traveled. That's not how much it's displaced, but it's actually traveled 1 meter. So they want to know how far would it travel in 2.4 seconds. Well, if it takes 1.2 seconds to do this, then it's going to do that twice in 2.4 seconds, because 2.4 is double 1.2. So down and back twice. So down and back, it moves a meter. Do that twice, and it's going to move 2 meters. So the answer to number 7 would be 2 meters. All right, the next example I'm doing is on page 459, next page. And it says that they have this one that they did here for you, and then we have these 4 that we can do. So on this one, it says you have a 0.22 kilogram air track attached to a spring constant of 12. I believe this one was even in the PowerPoint. We simply plugged in the 0.22 in for mass, the 12 in for the spring constant, typed this on the calculator, and got 0.85 seconds. So going on and looking at number 8, it says if the mass attached to a given spring is increased by a factor of 4, by what factor does the period change? Well, we have our formula for period right up there at the top. Period is equal to 2 pi times the square root of m over k. And they're saying, what would happen if you increase the mass by a factor of 4? Well, if I increase the mass by a factor of 4, that means I'm going to multiply whatever m is times 4 compared to what it was. So I don't know what the mass was, but whatever it was, now I'm multiplying it times 4. So how will that affect the period? Well, I know the square root of 4 is 2, right? So the square root of 4 is 2. That's going to make this whole thing come out to be 2 times bigger, right? Because I'm going to end up, think about doing it here without the 4, which is basically what they're saying, if you increase it times a factor of 4. So if I did it without the 4, and then I did it with the 4, then this result's going to come out 2 times bigger than this one, because this one had that 4 there. So if I multiply the mass by a factor of 4, that's going to make my period twice as big. So what's it going to do to the period? It's going to double it. By what factor does the period change? You could say by 2, or you could say that it's going to double. All right, so number 9. If the mass and the spring constant of a system are both doubled, does the period of the system increase, decrease, or stay the same? So this time they want me to double the mass and the spring constant. So originally, I don't know what it was. Originally, I'm just calling it m and k. But whatever it was originally, now I have to double both of those. So now I'm going to have twice the mass, and I'm going to have 2 times the spring constant. So by doing that, how will that affect the period? Well, you guys know from math that any number over itself is equal to 1. That's equivalent to a 1. It's going to cancel out, and I'm going to have exactly the same thing I would here. So if you double the mass and you double the constant, they cancel each other out, and you end up having the exact same effect on the period as you would here. So does it increase, decrease, or stay the same? It's going to stay the same. All right, so number 10, a 0.32 kilogram mass attached to a spring undergoes simple harmonic motion with a frequency of 1.6 hertz. What is the spring constant of the spring? And then they give you a little hint here, using the formula T. Now, if I were you, they're giving you frequency. So if they're giving you frequency, why not use the formula for frequency? Because we know this is the formula for period, and I know frequency is the reciprocal of that. So I'll write the frequency formula here. Remember, just reciprocal means to flip over. So now I got 1 over 2 pi, and the k and the m trade places. It just flips over. So I now have this as a formula. I have a 0.32 kilogram mass, so I can plug that in for m. My spring undergoes simple harmonic motion with a frequency of 1.6, so I can replace F with 1.6. What is the spring constant of the spring? So I'm trying to find K. I'm trying to find the spring constant. So if I'm going to find K, I'm just going to go ahead and solve for K before I plug those numbers in. So if I want to get this K by itself, the first thing I should probably do is multiply both sides times 2 pi. If I multiply both sides by 2 pi, I'm going to have, and I should probably just do this on a bigger sheet so we've got more room. So I will do that. All right, so here's our formula on another sheet. Let's multiply both sides by a 2 pi so that we can get rid of the fraction, at least, of the 2 pi. So that cancels with that. And so now I'm left with 2 times pi times frequency equals the square root of k over m. And so anytime you want to get rid of a square root, how do you get rid of a square root? You need to square both sides. So we are going to square both sides. And so on the right side, I'm just going to be left with k over m because the square and the square root cancel each other out. On the left side, I'm going to have 2 squared is 4, pi squared is pi squared, and frequency squared. And now remember, I'm trying to get k by itself because they asked me for the constant. So if I want to get k by itself, I need to multiply both sides by an m. So those will cancel. So now I end up with k, my spring constant, equaling 4 times pi squared times m times frequency squared. So if I plug those numbers in that I was given, 4 times pi squared, my mass was a 0.32 kilogram mass, and my frequency was 1.6 hertz. So 1.6 hertz and that was supposed to be squared. And so now you go to your calculator and you type that in. All right, so if you type that in, you're going to get a spring constant of 32.3. So remember, the bigger the spring constant, the stiffer the spring. So we would probably say that's a pretty stiff spring. All right. So next on that same page, we have example 11. It says if you have a spring constant, you have a spring with a constant of 22, what mass should you attach to the spring so that its motion has a period of 0.95 seconds? And so here's our formula again, and this time they give us T, so this is a good formula to use, and they're asking us to solve for M. So we're going to take this formula, and we're going to actually solve it for M. So I'll do that on another sheet. So this time we have the period for T, the formula for period, which is 2 pi times the square root of m over k. So now I want to solve that for m. It's asking me to find the mass. So very similar to last time, this time I'm going to divide by 2 pi to get rid of the 2 pi, because that's what will make those cancel. So now I have T over 2 pi is equal to the square root of m over k. And just like last time, to get rid of a square root, you're going to want to square both sides. So now I'm going to end up with period squared over 4 pi squared equals m over k, because the square root and the square will cancel. I'm trying to solve for mass, so I want to multiply both sides by k. So now I will end up, these will cancel, and I'll end up with my mass equaling k times t squared over 4 pi squared. And so if we plug in the numbers they gave us, they told us that the spring constant was 22 and that the period was 0.95 over 4 pi squared. And when you type this in the calculator, you're going to want to make sure that that denominator is in a parentheses. All right, and once you type this in your calculator, you're going to get a mass of 0.503. 0.503 if you were doing 3 sig figs, and that would be in kilograms. And that is number 11. All right, I realized I skipped some problems back on 455 that we hadn't gone over, so I'm going back to that one. This one, a very first problem for the chapter, it says a bird flaps its wings 5 times a second, or you could even insert the word per, 5 times per second. What are the frequency and period of this motion? So think about what they told us. They said 5 times per second, so you can think about that as a cycle, 5 cycles per second, whatever the case. But anytime seconds is on the bottom, that means we're talking about a frequency. So what they have given you is a frequency. So my frequency is equal to 5 hertz. Hertz are just simply number of cycles per second. There are 5 cycles per second. So period is the reciprocal of that. Period, we use the letter T. The reciprocal of 5 is 1/5. So that means there's a 1 second per 5 cycles, or 1/5 of a second per cycle, however you want to think about it, per time. And that's number 1. All right, let's look at problem number 2. If the frequency of a motion's doubled, what happens to its period? So whatever a frequency is, whatever my frequency is, I'll just use some weird little, let's say, C. So frequency is C, and it's saying that I'm going to double it. So if I double it, that means now my frequency would be 2C. And so how would that affect the period? Well, period is the reciprocal, so that would be 1 over 2C, right? So it's a half of what it was. So if frequency's doubled, that cuts the period in half. All right, number 3. The concert A string on a violin oscillates 440 times per second. If we increase the frequency of these oscillations, what does that do? Does the period increase, decrease, or stay the same? So remember, period and frequency are inverses of each other. As one goes up, the other one goes down. So if you're going to increase frequency, then that's going to decrease the period always. They're always inverse relationships of each other. The amplitude is the only thing that doesn't change the frequency or the period. All right, number 4, a tennis ball is hit back and forth between 2 players. It takes 2.3 seconds. 2.3 seconds for the ball to go from one player to the other. What are the period and frequency of the ball's motion? So what did they give us? They gave us 2.3 seconds per cycle, basically, 2.3 seconds. So remember that whenever seconds is on top, that means we're talking about when seconds is on top, that means we're talking about the period. Frequency is on bottom, period is on top. So the question was, what is the period? Well, the period's 2.3 seconds. They gave us that. Now, what's the frequency? Well, frequency is the reciprocal of the period, so that would be 1 over 2.3, 1 second per 2.3 cycles, which would be in hertz, and you would type that in the calculator because it's not considered acceptable to leave a decimal within a fraction. So 1 divided by 2.3 comes out to be 0.43. So that would be 0.43 hertz. 0.43 hertz would be your frequency. All right, so this is on page 461 in your textbook. And example 13.4, it says when a 10 kilogram mass is attached to a spring, the spring stretches 0.2 meters. Find the period of motion when this mass spring system oscillates. So keep in mind what they're giving you here. They're telling you the mass, which is great. I need to know mass. They want me to find the period, so they want to know T. But they do not give me K, the spring constant. But they do tell me X, the distance that the spring stretches. So this formula does not use X, but remember the one that does. We've been using Hooke's law all along. And Hooke's law says that force is equal to the spring constant times X. So if I want to know the spring constant so that I can use it in that other formula, I simply need to take force divided by X. So to get K by itself, divide by X. And let's see, I don't know the force, but could I calculate that force if I know mass? Because the force on this would simply be a gravity force. So I could just simply replace the F with an mg, which is what they're doing right here. They're replacing the F with an mg because we know m. And so now if you calculate that, you're going to have mg divided by x, and your m is 0.10, so you take 0.10 times 9.8 and divide it by x, which is 0.2. And then if you type that in the calculator, you should come up with 4.9 for your spring constant. And so now that I know the spring constant, I can plug that in here. So now I know the mass was 0.10. I know the spring constant was 4.9. So I simply type all that in the calculator, 2 times pi times the square root of 0.10 divided by 4.9 to get the period, which comes out to be 0.9 seconds. All right, so on that same page, we have some more problems we can do. I'm going to come down here and do number 20. Okay, so if you look on this page, number 20, it says it takes a force of 12 newtons to stretch a spring 0.16. So this time they actually did give you the force, but it says what is the period when a 2.2 kilogram mass is attached to the same spring. So remember, the spring constant doesn't change no matter what force you're applying to it. So I can use this to find the spring constant. Remember that. Force is equal to K times X. And in this problem, the force was 12 and the spring was stretched 0.16. So 12 Newton force stretched 0.12 meters. So if I divide those, that was a stretch of 0.16, not 0.12. All right, so I simply need to divide those to find my spring constant. So that gives me a spring constant of 75. So talking about a pretty stiff spring here. All right, so now I can go back and use that K value in my formula to calculate frequency and period. So letter A says what is the period? So remember that period is 2 pi times the square root of K over M. Oh, I'm sorry, it's M over K. That's my formula. So what is the period when a 2.2 kilogram mass is attached to the spring? So put 2.2 here, put my 75 here, and type it in the calculator to see what you get. All right, so when you type that in your calculator, you're going to have 2 times pi times the square root of 2.2 divided by 75, and that's going to give you 1.08 seconds for your period. All right, so moving on to letter B, what is the frequency of oscillations in this case? Well, you don't need to go through the formula again for frequency. You know frequency is simply the reciprocal of period. So if you know period, frequency is 1 divided by the period. They're reciprocals of each other. So 1 divided by 1.08. And if you type that in, 1 divided by 1.08, you will get 0.926. So frequency of 0.926 hertz. And that's all of your examples for this lesson.